Okay, we're back. This is part 2 now. Part 2, we're going to talk about the water itself. We were talking about the lakes and their measurements. Now let's talk about the water in the lake. And the first thing we're going to talk about in this part are physical water parameters. So things like light, turbidity, and temperature. And these are going to be the three things that are going to be most important if you're talking about fish. Okay, let's talk about light in lakes. It's, of course, very important because this is where photosynthesis starts. And just like any other ecosystem, you've got to capture that sunlight energy so that you've got energy for the remaining organisms in the community. So, what happens when light hits the surface of a lake? Okay, so you've got a surface of a lake, and you've got a photon of light coming down, and it hits the surface of that lake. Well, there's a couple of things that can happen. So let's break this down step by step so we can think through all the important parts here. That photon of light can be reflected, it can be scattered, or it can be absorbed. So let's talk about each of those in a little bit more detail. So the light that hits the surface of a lake can just bounce off, and that's it. That photon of light just goes somewhere else and is not part of the lake. It does not actually go into the lake ecosystem. And that's kind of important because we need some of that light to get in there. And you know this happens because if you've ever looked at the surface of a lake, you get glare, right? That's light reflecting off the surface of the lake. And so we're kind of curious what can influence how light reflects off the surface of a lake, because you know, if there's too much light reflecting off, then there's not enough left for the ecosystem. So what kind of things influence reflecting of light? The sun angle is going to be really important. So like right now, it's about noon, the sun is straight down, those photons of light are going straight down, and they're not likely to reflect. They're going to shoot right on in. But at dawn and dusk, when the sun is very low in the sky, now those photons of light are coming in at an angle, and they're much more likely to skip off. Another thing that really influences how much light is reflected is wind action, or waves. And so if you've got a nice flat surface, a lot of times the photons can go in easier. If you've got a lot of rippling on the surface, then it's more likely that the photons are going to bounce off. And another thing that we like to talk about in fisheries is ice. So in the winter, if you've got ice on the lake, does that cause more light to bounce off? And if it's just ice, the answer is no. Nice ice, clear ice, acts pretty much like water and will let those photons of light in. So you can get photosynthesis underneath the ice, and you can get oxygen production underneath the ice. Now, some things influence that, and it depends a little bit on how the ice was formed, and sometimes if the ice forms with tons of little small bubbles, well, then that can change things. But most of the time, typical ice is going to let most of the light in. However, if you have ice and snow, if you've got, say, 6 inches of snow on top of that ice, 10 centimeters or so, then that can cut down the amount of light by 95%. So it's that snow that really causes that light to be reflected off in the winter. And this is when we sometimes get winter kill conditions, because the light cannot get into the lake, so you don't get photosynthesis, you start to run out of oxygen, and you can get fish dying. And that's maybe not as common down here in the south because it doesn't freeze as hard, but I've seen this happen up north. Okay, so let's say that the light doesn't reflect. It actually does get into the lake, all right? And that's good because we want that energy in the lake. Now, what can happen to those photons of light once they get into the lake? Well, they can either be scattered or can be absorbed. So think about it this way. That photon of light gets into the lake, and basically what it's going to do is it's going to bounce around until it either bounces back out of the lake or it gets absorbed by something. And so, photons of light can get absorbed. You know this. This is how photosynthesis works. This is how things heat up. A photon of light gets captured by a molecule. The photon disappears. It turns into heat. It moves electrons around. Whatever can happen. And so these two things are very important to the fish in the lake. Let's talk about scattering first. So how much the light scatters in the lake is called turbidity. All right? So the photon gets into the lake and then it bounces off of stuff. And if you've got relatively clear water that doesn't have much stuff in the water, there's not much stuff for the photons to bounce off of, and so you have low turbidity. But if you have very muddy or dirty water, if there's lots of things in the water, then that photon of light can hit those things and bounce off, and then hit something else and bounce and get scattered around. That's what turbidity is. It's measured in things called NTUs, which are nephelometric turbidity units, and that's because the proper way to measure turbidity is with something called a nephelometer, which measures the scattering of light at a 90-degree angle. Sometimes your unit will read in FTU, which is Formazan turbidity units. They're basically the same thing, just one calibrated toward the other. But the idea is that if you have clear water with not much in it, then the light does not bounce around much. That's low turbidity. Lots of stuff in the water, the light bounces around a lot, and that's high turbidity. Well, that turbidity can become important because it influences what ultimately happens with that photon. Because ultimately, that photon's got to go somewhere. And it could get scattered and then bounce right back out. And it's no longer available for the organisms in the lake. Now, you know this is true because you've looked into a lake before and you've seen fish swimming or you've seen the bottom. Well, how do you see things? Light has to bounce off of them and go into your eye. And so if you're seeing a fish, light had to hit that fish and bounce back up to your eye. So you know that some photons of light go in and come right back out. But depending upon the water clarity, those photons go in, they bounce around, and then ultimately, if they don't leave the lake, they have to be absorbed by something. They can't bounce around forever. And of course, every time they bounce around, they give off a little bit of energy as heat. But when they get absorbed, then that turns into a lot of heat, can be used completely as heat, except in photosynthesis. Okay, so what absorbs these photons? The number one thing is the water molecules themselves. So the water molecules are in the lake, and the photons are bouncing around, and a photon eventually hits a water molecule just right, and the photon disappears. But where does the photon go? Well, first law of thermodynamics, energy is neither created nor destroyed. So the energy, that photon is a packet of energy. It has to go somewhere. Well, it goes into that water molecule, and it basically gets turned into heat and increases the kinetic energy of that water molecule. So that water molecule starts to vibrate a little bit more, and it heats up. And so when the sun shines on a lake, what happens? The lake gets warm. This is one way how. So the water molecules themselves can absorb a lot of photons. Molecules that are dissolved in the water also can absorb these photons. And there's things like dissolved organic carbon. There's lots of stuff dissolved in water, right? The water in a lake is not distilled. There's lots of things in it, and there are things that are broken up and they're dissolved in the water. Those molecules too can absorb photons of light. And what's interesting is that different molecules absorb different wavelengths. So depending upon what's in your water can influence what wavelengths of light are getting absorbed. And remember, these photons that are coming from the sun, they each have their own wavelength. There's a ton of different wavelengths, and those wavelengths have different energies and act differently. We can also talk about suspended things in the water. So these are things that are also in the water, but they're not dissolved, they're intact. And there's lots of molecules like that too, suspended particulate carbon. But what we're really talking about here is phytoplankton. And so you've got the algae that are in the water. They're photosynthetic organisms, and they will absorb particular photons of light of a particular wavelength and capture that energy in a chlorophyll molecule, use that energy to fix carbon, and then that energy and that carbon becomes available for the rest of the ecosystem. So light comes in, bounces around until something absorbs it, or it bounces back out. All this together we call attenuation. Attenuation is a diminution of light with depth. And so as you go deeper in a lake, you get less and less light for these reasons. That it's just unlikely for light to penetrate very deep. It's either going to bounce off of something or be absorbed by something the deeper you go. And that's called attenuation. And so let's look at, let's talk about this. If we go deep enough in the lake, the light is so attenuated, there's not enough left to drive photosynthesis. So up at the surface, you've got enough light, you can drive photosynthesis, but eventually you go deep enough, it stops, and that's the bottom of the euphotic zone. Remember from the last lecture, we said you've got the euphotic zone, which is where photosynthesis takes place, or the trophogenic zone, and then below this is the tropholytic zone, where you don't have photosynthesis. Well, where is that cutoff point? It's at 1% of the incident light. Excuse me. So as long as at least 1% of the light that hits the surface is still available, that's enough to drive photosynthesis in the phytoplankton. Excuse me. But less than this, you cannot drive photosynthesis. Now there's another term that's thrown about called the compensation point. The compensation point is where the rate of photosynthesis exactly equals the rate of respiration. So there's no net fixing of carbon at this point or below it. This is not the same as the bottom of the euphotic zone. At the bottom of the euphotic zone, you can have photosynthesis, but it's not as great as respiration. The respiration is actually greater, and so you're actually losing carbon, but you're still able to fix some carbon. So some people use these interchangeably, but they're not really interchangeable. Now, remember we talked about the Secchi depth as a way to measure water clarity, and it's roughly related to turbidity. But the neat thing about Secchi depth is that it's closely related to the bottom of the euphotic zone. So if you take the Secchi depth and you multiply it by 2.7, that will approximate the bottom of the euphotic zone. And so a lot of times people will just take a Secchi depth, multiply it by 3, and have a rough idea of how much of the water column is actually got light to produce, to drive photosynthesis. So there you go. Now here is a graph showing how light gets attenuated at different wavelengths. So study this graph for a little bit. The graphs we use in limnology sometimes are a little backwards to people. Usually we have the independent variable on the x and the dependent variable on the y. In limnology we often flip these because our independent variable is depth, and so we want to represent depth like the depth of a lake. So if you look at the y-axis, that's actually depth, and it's reversed. So 0, instead of being down at the origin in the lower left corner, it's in the upper left corner. Again, this is so you're looking at the lake like you're looking at it from the side. So the top of the graph is the surface of the lake, and the bottom of the graph is the bottom of the lake. So that's why we do it that way. And in these graphs, you see you've got depth, and then you've got the percent of incident light. So how much of the light that's hitting the surface still remains at that depth, but it's broken down by different wavelengths. You see blue, green, violet, yellow, orange, red. Now the graphs show the same data, it's just the bottom one is logarithmic. That's why you got straight lines. The top one is not logarithmic. So study these graphs, and let me ask you this. Which color of light penetrates the deepest, and which color of light penetrates the least deep, the shallowest, for lack of a better word. Well, you can see that the blue wavelengths penetrate the deepest in the lake. And that's why lakes look blue, because there's lots of blue light that's still available. And if you look at the red wavelengths, these get absorbed almost immediately. So if you go down just a meter or so, there are hardly any red wavelengths left. They get absorbed quickly and turned into heat. Now, I want to make a clear point about this graph here. This graph is just water. This is not a typical lake that has dissolved substances and has phytoplankton. All those things are also going to affect what wavelengths of light are in the water and how deep they go. This is just the water itself, the water molecules themselves absorbing wavelengths of light. So water absorbs red and infrared very well, and that's what heats up a lake. That's why the surface of a lake can get very hot very quickly, because all those red and infrared wavelengths get absorbed by the water molecules themselves right as soon as they hit. And again, the blues don't get absorbed very well, and so they kind of persist in the water, and that's what gives water its blue characteristic. If you're a scuba diver and you're down deep and you're taking pictures, you have to compensate for this, because certain wavelengths of light do not exist down there, and so you take a picture, it doesn't look very good to your eyes because you're missing some wavelengths of light. Okay, last thing we need to talk about is temperature, and how does temperature affect a lake. And we could talk about this for a long time, but I'm just going to give you the gist of it here. Before we talk about the distribution of temperature in a lake, we have to talk about the relationship of temperature and density. And in most things, as they get hotter, they get less dense, and as they get colder, they get more dense. And water is the same to a point. Now, if we look at this graph here, on the left you have the density, or the relative density of water, and then on the axis across the top you have the temperature. And you see it's a real funny shaped graph, but if you look at temperature of -5, you see that the relative density of the water is very low, much lower than the other values. You see there's a break in the line there. Well, of course, if the water is -5, what is it? It's ice. And we know that ice has a very low density. That's why ice floats. Now, as the water warms up, you see at 0, it's a little bit more dense, but it still has a lowish density. And again, 0, the water is still kind of ice and it floats. But then as the water warms up, it gets actually even more dense, until you get to 4 Celsius. And I talked about this the other day, that 4 Celsius is the maximum density of water. And so here, from ice to 4, as it gets warmer, it actually gets more dense, which is not what you would expect. But that's because the ice, the water molecules, form this lattice to where the molecules can't get close to each other because of the chemical properties. And so it makes the thing less dense. And as it warms up, that lattice starts to break up and the molecules can pack in a little tighter, which makes them more dense until you hit 4. And then, as you get warmer from 4, now the molecules are moving so much they can't pack in as tight anymore. And as you would expect, as the water gets warmer, it gets less and less dense. Okay? And it's this unique property of water, which is pretty nice, because if water didn't do this, if water just got denser as it got colder, then ice would sink and lakes would freeze from the bottom up and nothing could live. Now here's what I want to point out too. If you look at the graph on the right, this is the density difference per degree lowering. Well, what does that mean? That means for a change, for the same change in temperature, how much does the density change? And if you look at the first graph, you see it's nonlinear. It's a curve. And so when you go from 5 Celsius to 10 Celsius, that's a 5 degree increase in temperature. the density does not change that much. The water gets less dense as it gets warmer, but it's not that big a deal. It does not change that much. But look at when you go from 30 to 35, or say 25 to 30. It's the same 5-degree change in temperature, but look at the radical change in density. This is another unique property of water. Well, I don't know if it's unique to water, but it is something that helps us explain what goes on in lakes. Is that warmer water changes density faster. Now look at these graphs and convince yourself that that's true. Okay? So if the water warms up from 5 to 10, the density does not change very much. If the water warms up from 25 to 30, that's a radical change in density. And so at warmer temperatures, if the water heats up just a little bit, that's still a big change in density, and that can have cascading effects, which we'll talk about now. Okay, so we've talked about how temperature can cause a lake to stratify. Remember the different zones based on temperature. We got the epilimnion, the metalimnion, the hypolimnion. Well, this is based upon this temperature-density relationship. And we could go into a lot of details on this, but let's just talk about it briefly here. Let's start by looking at a typical dimictic lake, meaning it turns over twice, mixes twice, in winter. And here we've got ice at the surface, and of course that's at 0 C, and that's at the top. And the rest of the lake is about 4 to 10 C. But the whole lake is the same temperature. And since it's the same temperature, it can mix. There's no stratification, and water just can mix very effortlessly because there's no difference in density. If you get a difference in density, it's like oil and water. That's why oil and water don't mix. Oil has a much lower density than water, and the oil always floats to the top. But here, all the water is the same temperature. It mixes very well. But it doesn't, it has the potential to mix well. But it doesn't mix very well because you got that cap of ice on there. And so there's no wind action to help stir it. There's no reason for it to mix, but it can mix. Now let's go and look at the temperature profile. And this is another typical kind of graph that we're going to look at. Same deal. Y-axis is the depth from 0 to the bottom of the lake. X-axis is the temperature. And you can see how this represents what I just told you. At the very surface, the water temperature is 0 because it's ice. But then you go below the ice, the water's a little bit warmer, but it's isothermic. It's the same temperature from top to bottom. All right, now let's move into spring. Now spring, we have lots of mixing, and they call that spring turnover. When the lake mixes and the bottom water and the top water mixes, and that brings up nutrients from the bottom up to the top where the phytoplankton can use them, and oxygen from the top gets stirred down into the bottom, and you've just got this big lake, and it's all the water is just it's not a violent mixing thing, but chemicals and phytoplankton and things can move easily because the water is mixing. Now there's a couple of reasons why the water is mixing like this. One, again, it's all the same temperature. And if it's the same temperature, it mixes very easily. It doesn't take any energy to mix the layers. Two, think about spring. You've got a lot of wind. You've got a lot of rain. You're putting a lot of energy into that lake, and that energy can physically move that water and mix it up. And if you look at a spring temperature profile, you see it's pretty similar to the one we just looked at. It's isothermic from top to bottom, but it's shifted, it's warmer, because it's spring and it is getting warmer. Okay? And so that's what spring turnover is going to look like. Now if we go into summer, summer is where we see this thermal stratification. In the, here in the northern hemisphere, and it depends upon the lake, it depends upon the situation, but this is pretty typical. It doesn't happen really in Kentucky Lake because Kentucky Lake is a dammed river and it's constantly flowing. You've got that extra energy mixing it. There are places in Kentucky Lake where we can measure thermal stratification. But in a lot of typical reservoirs, in the summer, you're going to get an epilimnion, a metalimnion, and a hypolimnion. But you see that epilimnion is very warm, and so it's not very dense. The hypolimnion is very cold, and it's very dense. And that's why the warm water is on top and the cold water is on bottom. And the important thing here is that they can't mix. Now you've got like oil and water. Remember that that top layer is warm and not very dense. And so even if the wind's blowing, even if it's raining, that top layer and that bottom layer won't mix. And it's like you have two lakes in one. You've got that upper epilimnion, which is warm, and it's got light, and there's phytoplankton, and that's where all the organisms live because there's oxygen. Down deep, there's no light, so there's no oxygen produced. It's cold. All you have is waste products and dead organisms raining down, so you have some organisms breaking those down, but they're actually consuming oxygen, no oxygen being produced, so it tends to lose oxygen down there at the bottom. A lot of organisms can't live down there because of that reason, and so you've kind of got two lakes. So a lot of the fish are going to be squeezed into that upper layer because there's not enough oxygen down there, and also a lot of fish are sight feeders and they could use light. So summer stratification is going to look something like this, and you can see a very radical change in temperature as you go down with depth. So at the very surface it's very warm, a rapid decrease in temperature at the metalimnion, and then it's isothermic down to the bottom in the hypolimnion. Now how do we get to here from the previous graph? We've got spring where everything is the same temperature, and now you get this. Well, it all depends upon nice sunny spring days, kind of like what we're having here. And so you've got the temperature in the spring that's all the same from top to bottom, but you get a bright sunny day that heats up that surface water, but since it's heated up, it's lighter, and so it stays at the surface. That heat does not get mixed down into the lake very well. So the next day, when the sun comes up, that sun is heating up the exact same water molecules that it heated up yesterday. And so now they get even hotter. And as they get even hotter, they get even less dense. So they're even less likely to mix down into the lower layer and mix that heat in. And then you come to the third day, the sun comes up, now that water's starting to get really hot. You get this positive feedback loop in which those surface water molecules just get heated more and more and more. Remember, as that water temperature gets hotter, just a slight increase means a radical difference in density. And so you get this kind of runaway thing where the top layer just keeps getting hotter and hotter and hotter because it just keeps absorbing sunlight energy. That bottom layer never gets that sunlight energy. The two get less and less likely to mix. That's how you get stratification. Finally, now summer starts to cool off. That epilimnion starts to cool. It starts to radiate that heat. At some point, that epilimnion cools to the same temperature as the hypolimnion. Now they're the same temperature, which means they're the same density. What's going to happen? Now they can mix, right? Again, in the fall, you tend to have more storms. You have more wind, which helps to start that mixing process, and that's what we call fall turnover. Again, it's isothermic, so the layers can mix. Now you've got that hypolimnion, which sometimes is anoxic, which has got a lot of nutrients. It gets mixed up with the upper layer, and that's fall turnover. And it's going to look very similar to spring turnover, about the same temperature, isothermic from top to bottom. How this works a lot of times depends upon how long it took for stratification to set up in the spring. We could talk about this forever. So this is the idea. This is how temperature varies both spatially and temporally in a typical lake. And of course this is going to have impacts on the rest of the organisms in the lake, especially the fish. And so that's it for the physical properties of water. Coming up next, I'm going to talk a little bit about the chemical properties of the lake water. So I'll see you in a bit.